Okay, so to start with this problem, we have the two numbers m and n, right? And they're equal to p to the 4, where p is a prime greater than 3. So my very first thought, as you should with any Olympiad problem, is to play around a little bit. So let's take the first prime greater than 3, 5, and say 5 to the 4 equals, of course, 625, right? And we want to do something with 625. So we want the LCM of two integers plus the greatest common denominator of those two integers, or greatest common divisor, highest common factor, whatever you want to call it, to be equal to 625. So now we've got something to work with here, right? What could we do with these two to try take something useful out of the fact that this only has one prime factor? So firstly, I want to think a little about what the lowest common multiple and highest common factor actually mean. So if we take two random numbers, right, say 3 and 4 for the sake of this example, we know their LCM is equal to 12 and their GCD is equal to 1. So that means their coprime and also if they're coprime, their lowest common multiple is simply their product. But now, if we were to consider, so this is, of course, for 3 and 4, if we were to double both of those to get 6 and 8, then their lowest common multiple becomes 24, right? Even though there's technically been two multiplications by 2, the lowest common multiple is doubled, and the highest common factor is also doubled. So, um, now that we've gotten somewhere with this, there's one thing that we always want to note, right? And it's that the lowest common multiple will always be divisible by the highest common factor, right? This is quite, like, we can generalize this very easily. If you think of this as, let's say you take m as being, what should we do? We'll do a to the x, b to the y, and then we take n as being c to the z, a to the w, right? Their highest common factor will be the smallest power of a. So a to the w if w is less than x, or a to the x. And of course, their lowest common multiple will be the larger one of these, plus c to the z and b to the y. Plus, you get the idea. So, what can we do with this? Well, we know that there will always be this shared term between the lowest common multiple and the highest common factor. And we want to take it out. We want to divide by that term. In fact, we know that term is always going to be the highest common factor, right? So, for now, just for the sake of convenience, we'll say h equals hm of n, l equals lm of n. We can write this, l plus h equals p to the 4. We can actually take out a factor of h, l over h plus 1 equals p to the 4. Well, yeah, equals p to the 4. Okay, well, we've gotten somewhere already, because now we've got a product equal to a prime to the 4. So, of course, a p to the 4, just as a number, only has so many constituent parts. It's made up of a 1, a p squared, p cubed, and a p to the 4. Okay, so now we can consider the different cases of h to result in this product being even vaguely functional, right? So for example, we take h equals 1, right? We'll work in order, as you should. If h was to be equal to 1, then we have l over 1 plus 1, so l plus 1 equals p to the 4, right? Which means l is equal to p to the 4 minus 1. And then, yeah, we'll build on this in just a second. For now, though, we'll keep this case by itself. If h was to be equal to p, because once again, we're going through this list, and we're working with h, l over h plus 1 equals p to the 4. So if h was to be equal to p, then we have l over p plus 1 equals p cubed. And, you know, we can keep working on this. It's not all too bad. We get L over P squared plus 1 equals P squared. And then we get L over P cubed plus 1 equals P. The final thing I want to say, if we have L equals P to the 4, then we end up with L over P to the 4, or sorry, H equals P to the 4. We end up with L over P to the 4 plus 1 equals 1, which this leads to this statement, which is invalid. So we know that H cannot equal P to the 4. Okay, well now we've got quite a lot more to work with. So for now, how are we going to work with it, right? I want to first consider that very first case where we have H being equal to 1, so the two numbers being coprime. If the two numbers are coprime, you end up with L plus 1 equals P to the 4, right? So what do we do with this? Well, we have L equals P to the 4 minus 1, and we want to get, so L, remember, is the lowest common multiple of two numbers. We can immediately, you know, do the typical factorization of this just by applying difference of two squares twice. But we need to note that this will have some number of prime factors, right? This number, P to the 4 minus 1. You can write it however you want. For now, we'll just say L is equal to P1 to the E1, P2, E2, etc., right? So if this was to be the lowest common multiple of two numbers, well, of course, these powers would need to be part of the two numbers that this is the lowest common multiple for. But there's an important thing to note here. The greatest common denominator we said was 1. We said where h equals 1. So that means they cannot share any prime powers. Like, for example, let's say this was the number. It only had these three prime factors. A valid combination would be m equals p1 to the e1 and n equals p2 to the e2 multiplied by p3 to the e3, right? This is valid. But m equals p1 to the e1 minus 2, n equals p1 squared multiplied by p2 to the e2, p3 to the e3. This is invalid. Even though this has the correct lowest common multiple, it's still invalid because the highest common factor is then a different number. So then, what progress have we made? Well, we know that the lowest common multiple is equal to p to the 4 minus 1, and the number of distinct prime factors that this has is going to give us a very easy link to the number of pairs. So, for example, let's say you take p equals 5, just hypothetically, right? You end up with this equal to 624. You know, we can decompose this. So this is divisible by 4 immediately. You get 1, 5, 6, and 4. This is also divisible by 4, 39 and 16. So you get 3, 13, and then 2 to the 4, right? As we said earlier, it's going to be the number of distinct prime factors is going to have some relation to the way we can split it, because we have m and we have n. We're just told they're positive integers, so one of them could be 1. But yeah, we can distribute these either way. As they're ordered pairs, it doesn't really mean, like, it means that you can't. So for example, if m was to be equal to 3, n was to be equal to 13 times 16, swapping them around would lead to the same result. So, okay, now we need to figure out how can we distribute these. This isn't all too hard, because once again, the symmetry is already done for us. So we can say if m was to be equal to 3, then n would have to take the other two. If m was to be equal to 13, n would have to take the other two. M was to be equal to 16, n would have to take the other two. Or m could be equal to 1, and then n would take all three. So if we have three prime factors, this would lead to 4 different combinations between m and n. Okay, now let's consider a few different cases, right? For now, this is the important thing that we've spotted so far. The number of prime factors is what will lead to the correct number or incorrect number of ordered pairs, depending on how you look at it. So, okay, for the other cases where we end up with L over P equals P cubed minus 1, of course, in this case, the highest common factor of m and n is p, right? Then we need to notice something, right? Something kind of important here. If the highest common factor of m and n is p, that means both of them have at least a factor p. So m, once again, if we were to express it as p1 for e1, etc., we know that this would have at least one of these would be a p, which means when you multiply m and n to get their lowest common multiple, you end up with this having a factor p, which means that this would be an integer, and at least so far, this is valid. So we now know that this, at the very least, will have the factor p. So this will lead to another number, right? Call it whatever you want. We'll say it's v, right? P cubed minus 1. The thing I want to note here is that this will lead to a very similar outcome. If you remember when we were working with the LCM of 3 and 4 and the LCM of 6 and 8, and they ended up being exactly double each other, right? So this became 12, this became 24. We can work in a very similar vein here in that v is going to be the lowest common multiple of m over p, n over p, right? And again, we end up with a very, very similar story because whatever numbers we end up here, we can just multiply by p to get to m and n. So, once again, we're going to try with 5, just for the sake of example, and we end up with v equals 124. This can be factored. Immediately, you'll think of 31, comma 4. We know 31 is prime, so we have 31, 2 squared. Noting that both of these will need to be multiplied by p, we can essentially ignore it and just think, how are we going to split these? Well, there's two ways to do that. You either have m equals 124, n equals 1, or we have m equals 31, n equals 4, right? And we can swap them around, but we've been told not to count that. This leads us to two outcomes. Right now, we're working in the case n equals 5, or sorry, p equals 5. I'll explain why we're doing that in just a second. For now, though, we march on with L equals P squared, or L over P squared equals P squared minus 1. Exact same idea. This time we're going to get a different number. We can call it U. This is going to be the LCM of M over P squared, N over P squared, right? And then this is going to be equal to 24. 24, of course, is equal to 3 times 2 cubed. And we end up with another two outcomes from over here, right? Literally the same story as last time. Now, we can try L over P cubed equals P minus 1. Same thing, we've got L equals 4, and this leads us to one more outcome. So, what are we left with? Well, we've ended up with, in case you remember, 4, 2, 2, and 1. So if P equals 5, we have 9 ordered pairs. Now, we need to consider what happens next, right? What happens when P is equal to any number greater than 5? Well, we'll try for P equals 7 immediately, right? Just because, you know, next logical step. So 7 to the 4 is equal to 2401, right? So that means immediately we're going to try the case of h equals 1. So that means we've got 2400 that we need to factor. Of course, 5 squared to the 5, I think, and 3. This is also 3 prime factors immediately. And the thing I want you to notice, right, is if we look back to the prime factors we ended up with, 3, 13, 2, and 4, right? The next one, 31 and 4. The next one, 3 and 2 cubed. And the next one is just 2 squared. All of them are going to be divisible by 2. Any prime power minus 1 will be even for a p is great because p is greater than 3, right? So you can kind of skip that step when working with this. In reality, in this problem, we would analyze this the same way. This leads us to four combinations. 7 cubed, 343, we end up with 342 that we have to factorize. This is actually not a multiple of 4, so we can take a 2 out, you end up with 171, which is a multiple of 9. So this ends up with 19 times 3 squared. And immediately you notice we've ended up with more prime factors than we had last time. Last time we only had 2, now we've got 3, right? So immediately we know that this is going to lead to another 4, and this isn't going to be a possible solution when p equals 7. So we just need to consider the nature, how will this continue as the size of p increases? Well, as p increases, let's try again for 11, just for the sake of argument here. You end up with 121 squared, which I don't actually know off the top of my head. But if we do that, we end up with 1, 4, 6, of course, yeah, 14641. So now we've gotten way bigger in terms of the number, and you should ideally be able to see that this will have more prime factors, right? And as soon as we've got numbers such that the first one has more prime factors than, more than 3 prime factors, as in p to the 4 minus 1 has more than 3 prime factors, we know we've found our smallest answer. So if we work with this, we can divide it by 2 many a time, but we'll start. So 7, 3, 20, 3, 6, 60, 1, 8, 30, 9, 9, 1, 5. This can, of course, be divisible by 5, and that gets us to 183. 183 can then be divided by 9, which gets us... Oh, sorry, not divided by 9, divided by 3, which gets us 61. So you have 61, 3, 5, and some large power of 2. This is 4 prime factors. This will be greater, right? You can keep on working with this. The best way, of course, because we need to be mathematically thorough, this is an Olympiad, is to actually think, what are we doing with p to the 4 minus 1? Well, this is equal to p squared plus 1, p squared minus 1, which is equal to p squared plus 1, p minus 1, p plus 1, right? So we can very quickly spot that this is going to have, at least one of these is going to be a multiple of 3. There's going to be many a multiple of 2 in there. And importantly, for p squared plus 1, we can actually take something from this. I want you to think of this number, right? We can take a small p, for example 7, we'd end up with 50, right, for p squared plus 1. And we can immediately notice this has prime factors outside of 3 and 2. But is there any way we can prove that it has prime factors outside of 3 and 2? Well, for any p squared plus 1, right, we know p is greater than 3, and therefore we know that p does not equal 3. Or, importantly, p does not equal 0 mod 3. So p has to be equal to 1 or p equals 2 in mod 3. So if we do p squared, then we'll end up with p squared always equals 1 mod 3. What does that mean? Well, that means p squared plus 1 is always equal to 2 mod 3, which means that p squared plus 1 does not have 3 as a factor. So that means that p squared plus 1 is either itself a prime multiplied by some power of 2, where it is then multiplied by at least one multiple of 3 and some more powers of 2, which means that the minimum number of factors we could have is if this p squared plus 1 was to be a prime or a prime to some power, one of the two. If we look back at the case we analyzed where we had 5, p equals 5, we ended up with p to the 4 being equal to 13 multiplied by 3 multiplied by 16, or, well, 2 to the 4. As you notice, this was a prime. Well, should I say p squared plus 1 ended up being 13 times 2, and this factor of 2 was good, right? Like this just merged into that. That means that p to the 5 gave us the minimum number of possible options in terms of combinations of m and n. So if we look back to see the number of combinations we ended up with, of course, it was 1, 2, 2, 4, which was 9, which means that our answer to this whole problem all the way at the end is that the minimum number of k, the minimum value of k for different primes is k equals 9.